You're listening to the Land Use Podcast, brought to you by the Alberta Land Institute.
How many trees in the forest? That says a lot of the potential of the forest in restoring carbon. The ultimate objective is to predict the change in the carbon sink potential of the forest. The first question is, what is the potential? What factors contribute the potential? And how that potential will change over time in response to global change.
Hello and welcome back to another episode of the Land Use Podcast. My name is Aisha Wu with the Alberta Land Institute. Today's episode is about the biomass of boreal forests, but before we start, I would like to acknowledge that the University of Alberta, its buildings, labs, and research stations are primarily located on the territory of the Nehio, Niitsitapi, Métis, Nakota, Dene, Haudenosaunee, and Anishinaabe, lands that are now known as part of Treaties 6, 7, and 8, and homeland of the Métis. The University of Alberta respects the sovereignty, lands, histories, languages, knowledge systems, and cultures of all First Nations, Métis, and Inuit nations. In Alberta, boreal forests cover 60% of our land base. Understanding the biomass of these forests could inform climate-resilient action and policy. Fangliang He, a researcher here at the University of Alberta, is joining me today to discuss his research on boreal forest biomass. Thank you so much for joining me, Fangliang. Can you introduce yourself?
Okay, so my name is Fangliang He. I'm a plant ecologist. My interest in ecology spanned from theoretical ecology to application. So theoretical, what I mean here is to understand those mechanisms that maintain species diversity to application, like forest management, and the impact of climate change on forest ecosystems. 23 years ago, before I came to UVA, I worked as a research scientist in the Canadian Forest Service in Victoria. So that was really a long move. I hold a Canada Research Chair position at UVA in biodiversity and landscape modeling.
So you really are an expert in the field of Canada's forests, really.
Well, I know some of the system. For sure, that's my career, my job, I make a living on that. Forest is such a complex system. It varies, and it's context dependent. So it means it's a system that is elusive. It's difficult to understand. But forest ecosystem, now, when we look at the system, the changes, so we identify what are those main mechanisms, main factors which determine the dynamic, the change of the system.
Right. So for the past couple of years, you were working on research partially funded by ALI. What was that research looking at?
Okay. So that is the project aimed to quantify the dynamic, spatial temporal dynamic of biomass, forest biomass in Alberta. So when I talk about forest biomass dynamic, it means a change over time and over space, and also more important, to identify the factors which contribute the changes. Only understanding those factors, those processes which determine the change, can we better manage the system, predict the change of the system.
And part of that has been mapping tree density, is that right?
That is only one part of the project. So that is the further thing we look at. But the overall, the ultimate objective is to predict the change in the carbon sink potential of the forest. First question is, what is the potential? What factors contribute the potential? And how that potential will change over time in response to global change.
So what role did mapping tree density have in that?
Okay. Tree density. How many trees in the forest? That says a lot of the potential of the forest in restoring carbon. So more dense, larger trees, certainly the potential high is high. That's forest hold more carbon, more biomass compared to low density in the small trees. So it's very important to understand the density. That's the first step of the system and how the density would change. For example, in response to global change. So our work is not the first work to estimate the densities, but the previous estimation, there's a lot of a huge uncertainty, the huge variation. So we actually increase the accuracy. For example, previously based on global estimation, the estimate North America, that is the North America Boreal, that include the Canadian Boreal and Alaska. Together, they approximately like 211 billion trees across North America. Those trees, certainly when I refer say tree here, it means those trees with a diameter larger than 10 centimeters that do not count smaller trees. So our new estimation that is certainly much better, much improved estimation is we estimate 30% higher than that 210 billion trees.
Oh, wow. That sounds like a really positive finding.
Absolutely. It means the capacity of forest in mitigating climate change was underestimated.
Oh.
That's good
news.
News.
That's very good news. Yeah. So what does that mean then for biomass?
So biomass, here we refer to like a dry biomass, the weight of the timber. Well, not just the timber, include every component of trees, plants, including underground, like leaves, and also include debris.
Okay.
Yeah, those dead wood.
So when we last chatted with you during our webinar, we actually already spoke about the tree density research. So you've moved on to the next part, is that right?
Yeah.
And what are you looking at now?
So that's a part of the Alberta Land Institute project. So right now we're working on a number of things. The first things we look, tree height, how tree height growth respond to climate change. We are working on modeling, quantify growth rate, growth, mortality, and recruitment. Because, the three rates, growth, mortality, recruit, the three rates really determine the dynamic of a forest. Think of this. Even the forest is subject to the effect of many factors, but boil down, that three things, mortality, growth, recruitment, that determine the dynamic of forest. So we are looking for which of those three processes contribute most to the dynamic of biomass of forests. The mortality that reduce biomass, growth, and the recruitment that increase biomass. So this is really biomass forest is really subject to the balance of those three rates. Because some of the rates, like mortality, growth, recruitment, they may not have the same sensitivity to the same climate factors. For example, precipitation, temperature. They have a different response to those factors. So it's very important to identify how those rates change and how they respond to those global change factors.
That makes sense. So we know what potentially our forest could look like in the future. So how are you measuring those three variables?
The data we use basically is long-term, that's PSP, permanent sampling plots. Those plots across Canada, like in Alberta, the Alberta government, that's Alberta Agriculture and Forestry, and also industry, like Weyerhaeuser, West Fraser, they maintain many of those plots. So Alberta will roughly have over 2,000 plots, and also including other plots like ABMI. ABMI maintain about 1,000 a 20 by 20 kilometer grid plot cover across the provinces. So those, like a PSP, Alberta PSP was initially established in early 1960s. And every couple of years, government and the industry, they went back to recense those plots. So those data are very unique, really unprecedented data, offer a lot of power, the capacity to analyze the impact, the dynamic, impact climate change, and the dynamic of the forest systems.
Yeah, it's incredibly valuable to have data that goes back that far.
It's very unique, amazing data.
Yeah, that's fantastic. Do you have any findings you can talk about so far?
Yes. For example, tree height growth. So interestingly, initially we expect with the global warming, tree height growth may accelerate, increase growth. But we found actually this is very little impact on height growth. But in terms of growth rate, this growth rate is basically the increment of biomass, like those basal area increment. Biomass mortality decreases. Yes, we found mortality decreases. That is very sure. Growth rate, some area increases, some other areas decreases.
Oh, why is that?
It's a complicated issue. Let's look, for example, warming effect on growth. Warming, global change can increase drought. Drought is not good for growth. Drought decrease growth, right? This is, we call it climate change induced growth reduction. But on the other hand, warming increased temperature. That can stimulate growth. And also the causes of warming, the CO2 increase, right? CO2 increase, that is CO2 fertilization. It means more CO2 because photosynthesis needs CO2, water, and produce a carbohydrate, and water again, and oxygen. So CO2 basically is food for plant, for photosynthesis. So CO2 and the warming stimulate growth. That is increased growth. But climate change increased drought. Drought reduce growth. So it's not a simple linear effect. All those factors, they interplay, they work together. So at the end, in some area, you may see growth in stimulation. In other area, growth reduction. This also depends on species. Different species, they have a different sensitivity. They have a different response to different factors. For example, drought. Aspen is very sensitive to drought. So you would see aspen mortality increases, right? But for some other species, they're not as sensitive to drought as like aspens. So the global warming effect could be positive.
Interesting. It's not as simple as saying that, yes, there will be more growth or there will be less growth.
That's why there's a lot of controversial debate, even in scientific communities. It depends on what species you look at and where you look at, like a southern, northern regions. The response differs. Even like if you put this into a broader scale, like a temperate forest, boreal forest versus tropical forest, the species response is very different. On average, like in Canada, high latitude region, temperature increases more than twice warming average than like a tropicals. But the magnitude of temperature increase does not necessarily say the global global warming impact is high. It depends on species, the organism's thermal tolerance, because tropics temperature vary like a diurnal fluctuation, the range is very small. Those species adapt. They're used to such a very small thermal range. So even a small change in the tropics could be fatal to many of those species. So in our region, for example, our day-night temperature can be as large as 20 degrees. So species here are more tough. The thermal tolerance is wider. You can't simply just say, okay, because warming magnitude is high here, then would be more problem. It could be, but it's not as simple as that.
So what are your next steps?
So one of the huge uncertainty in terms of estimating carbon sink or carbon source, what I see is missing those small trees. Almost every research only focuses on larger trees, for example, tree larger than 10 centimeters. But in forest, in nature, small trees are the majority. Most of trees in forest are small trees. Larger trees are the minority. Even though they're large, they're big volume, but the numbers are small. So by missing those majority, even though the stem's small, we can miss a huge chunk of carbon. More problem is those small trees, they grow fast, and the mortality also high. So it means the cycling, the turnover time is fast. So this is something I'm going to look at. I'm working on developing models to estimate how many trees smaller than 10 centimeters, and then put this component of carbon into the estimation of the carbon sink and the source.
Okay, so then after mapping the biomass of trees, what other directions do you think your research will take?
Fire. This is something I would like to put into the equation to looking for the capacity of our forest in mitigating climate. So fire really has been, as we see, has been really a issue. So how fire would add another layer to this complex system. So how fire would reduce our capacity. That is something, we right now try to bring this two together. So I have some collaboration with the people from Ontario, Ontario Forest Research Institute. We have a project to look at that, to combine biomass dynamic and fire dynamic.
Yeah, wildfire is a really important factor. I'll be really interested to learn more about that. How do you think your research can be utilized?
Yeah. So for example, collaboration with Ontario government. So this is something that is in our research program. So we're gonna apply this to, we call the forest management unit. Some specified area, designated area that's subject to silviculture management. So, for example, thinning, prescribed burning, how this would reduce fire risk, and then that further relate to how the suppression of fire would increase the capacity of forest in storing carbon.
Absolutely, yeah. So how can other researchers build off of your work?
Yes, this is a very good question. The research I described here and funded by ALI, this addresses some very basic questions. For example, basic question to understand really tree species, forest ecosystem, how they respond to climate change. We really need to understand those ecophysiological processes. those traits and adaptation, species adaptation to species, like aspen, birch, spruce. They live here for so many years to adapt to environment here. So any change will have a fundamental effect to those very basic ecophysiological and evolutionary. This basically mess up or break down those evolutionary relationship with the environment. So it's a huge challenge. And it's a very basic question. Is how evolution and the ecophysiological and also biodiversity, how those things would change and the continued global warming, global change. So those are very basic things.
How could your research inform policy?
Policy has to be science-based. So what really science, the question, science answer is how that happens. For example, how a forest they respond to climate change. So this how is referred to the research I'm doing is how growth, mortality, respond to climatic factors, and which of those processes, which of those three rates contribute most to biomass dynamic. Only after you understand those how questions will you be able to make solid science-based policy.
Yeah, of course, that makes sense, because if we have a better idea of what the future might look like, then we can better prepare.
That's right.
What kind of challenges did you run into with this research?
I went through the literatures, a lot of inconsistent, even for a single number, like how much boreal forest we have. From a different report, a different publication. Some say the 270 million hectare, others say it's 360. Which one I should believe?
Those are wildly different numbers.
So almost a million hectare difference. And a forest always, like respiration, for example, to release carbon, like a fire burning, release carbon. There are also photosynthesis, absorb carbons. Some people say, okay, start 1990s. Canada's forest already become a source. Others say, no, they started become source like 2018. Still others argue, we're still carbon sink, but a weak sink.
Oh, that's interesting.
You can see that the uncertainty is huge.
Yeah, I imagine that makes finding your starting point really difficult.
That's right. And that's certainly become the problem for policy making. Should we say we are sink, or we are source, or we are becoming source, or we are still weak sink? So for different data, the policy has to be different. So that is a challenge what I see. Another challenge by going through this research, what I see is nature-based solution to climate change. Now, the particular challenge I'm talking about here, the forest management. For example, reduce fire risk. Well, research shows thinning, the silvicultural management, and prescribed burning is an effective way. But the problem is the economic feasibility, the operational side. How you can really implement thinning to such a vast forest. It's almost not possible, even though, yes, it can reduce the fire risk. So economically, well, I'm forester, but basically I don't think this really implementable to large area. So this also speak a bit how science can be better integrated with operation. This is often disconnected. Science theories, beautiful theories that may not necessarily feasible into the ground operation.
Yeah, that's a really good point. We are unfortunately going to have to wrap up the episode here, but before we do that, are there any concluding thoughts that you have?
Concluding thought, that's really a very personal experience. Having gone through this research over the past 2 years, my understanding, that's just really very personal understanding. As far as any system, it's not as simple as you initially thought. The more you work on, you find it more challenging to fully understand a system.
Perfect. Well, thank you so much for making the time to join us today, Fangliang. I really appreciate it.
Thank you. Yeah.
You can find out more about Fangliang's research from the links in the description. If you enjoyed today's episode, you can like, comment, and subscribe. You can also follow us on Facebook, X, Instagram, and LinkedIn, and sign up for our newsletter from our website, uab.ca/ali, to stay up to date with all of our latest podcasts, research, webinars, and more. Thank you for listening to the Land Use Podcast.